We will begin discussing energy methods right now. This is in chapter 6 of your book. I will follow a slightly different tactic than your author, but you'll be able to follow very easily. And then we have some really fun kind of head exploding examples at the end of the lesson. A couple of quick reviews. I know that you've had some exposure to energy methods already. Of course, we're going to only look at linear elastic problems. And real quickly, the degrees of freedom, of course, refer to independent geometric quantities. That's the key idea here. It could be a displacement or it could be a rotation. So when we're talking about beams, you recall that you could have a 6-degree of freedom beam, for instance, axial, transverse, and rotation at each of the two ends. We're also talking about the configuration of the structure after loading. So this is at the equilibrium time, not during the loading, but after the loading. And then as a real short aside here, in a truss, of course, each node has 2 translational degrees of freedom. And the displacements actually vary linearly, so it's a linear function between the 2 joints at either end of the bar. I don't know if you've ever thought of that or not. Okay, let's talk about work. Again, it's an idea that you're familiar with, especially from physics. Work is done by a force if it has a component parallel to the displacement of the particle, or if it has a moment component at the same sense as the rotation that we're investigating. So if we have a force F applied to a particle and the particle moves from A to B and it moves a distance d, but the F is at some angle, then we can apply the physics rule here for force and say that the increment of force dW is equal to F times cosine beta times an incremental displacement du. Okay? And then we integrate to find the total work here, which would be the integral of that expression that we just saw. So we're integrating F cosine beta, but very interestingly, we integrate over the length d. So from 0 to d, we'll need that for homework. So we're going to integrate that expression. And finally, just as an aside, F could be a function of beta. F could be a function of the displacement u, or the angle beta could be a function of u. So it's all doable. The math just gets a little more complicated. The F sine beta component does no work here. And certainly the work can be negative. So if beta is bigger than pi over 2 all the way down to 3 pi over 2, then the force would be opposing the motion and we would have negative work. And all of these statements can be restated for a couple that is rotating some point on a body through an angle theta. All right, so let's get into an example here that sounds, again, simple, but actually isn't. It's kind of a theme of our course. So when an elastic body is deformed by a load, energy is conserved. So we're not talking about accounting for heat or noise or anything like that. The work done by that load is not lost. It's stored as strain energy. And strain energy is a concept that you have seen in your mechanics course, but I'm sure it was just superficially touched upon. So we've got a linear spring, stiffness K, an axial load F, which causes a displacement U, and then it moves through some displacement D. So here's our displacement D, and at the final configuration, when we're in equilibrium, we have the little f becomes big F, and point A moves over here. It's displaced amount D.